Hello and welcome. This is a video series made to explain the concept of density of states. In the first part of the video series, we will look at what the word states means, and then we will visualize these states for a case of one-dimensional crystal lattice. The theory of density of states is derived from a problem from quantum mechanics, which is famously known as the infinite potential well problem. And the solution to this problem with the help of the time-independent Schrodinger's equation. As this is a topic on its own, I will directly use the results from this problem and its derivation. But if you are not familiar with infinite potential well problem, there are some links that I have attached in the description. So please have a look. Now let's model our one-dimensional crystal lattice. So the dots on this line represent the atoms and the line itself represents the lattice. Let's say the length of this lattice is L. The first result which we will be using is that the electrons act as probabilistic waves. So now we can model the electrons directly on top of this lattice as waves. So in this case, the horizontal axis represents the distance, while the vertical axis represents the electron wave function, which is also known as psi of x. And now we can draw waves, and so our electron waves can look possibly something like this. The second result which we will be using is that the value of the electron wave function is 0 outside this lattice as well as at the edges of the lattice. So it has a 0 value outside as well as at the edges of this lattice. And the third result is that the waveform of the waves is always sinusoidal. Now, using these three results, let's draw some waves and verify whether they can be called as electron waves or not. So, can this be an electron wave? Well, the answer is no, because its values at the edges are not zero. It has a non-zero value at this and this, both the edges. So it is not satisfying the second criteria. So this is not a possible electron wave. Can this be an electron wave? Although it is satisfying the boundary conditions, it is not a sine wave. So this is also not a possible solution. Now let's draw a sine wave and which has zero values at the boundary. Please assume that this is a sine waveform. So this particular wave has zero values at the boundary as well as a sinusoidal form. So this can be a possible electron wave. Okay. Now let's try to find what is the frequency of this particular electron wave. For that, let's draw this figure in a larger area. Now we can see that half part of the wave is occupied by the whole lattice. So the half of the wavelength is equal to the length of the lattice, which can be written as an equation as lambda by 2 is equal to L, which gives lambda as 2L. And the wave frequency, which is also represented by the k wave vector, which has an amplitude of 2 pi by lambda, will now become 2 pi by 2L, which is pi by L. Let's call this as K1. So this particular wave has a frequency of K1. Now the question is, what other configurations can the electrons be in? Or what other frequencies can the electrons have? So one of the possible solutions to this question is, if I have a wave of say frequency twice than that of K1, then let's draw this wave. So this will be the wave of double frequency than that of K1. As this wave had one lobe inside the length L, now the wave with double frequency will have two lobes. Now you can see that this wave is also satisfying both the criteria. It has zero values at the boundary and it also has a sine waveform. So this is also a possible electron wave function. Now let's draw a wave of triple frequency than that of K1. You can see that this wave of triple frequency is also satisfying both the criteria. So this is again a possible electron wave function. So now you can see where I'm going with this. For any wave which has a frequency which is integer multiple of this k1 will satisfy both the criteria. So that wave will be a possible electron wave function. For waves having frequency k1, 2k1, 3k1, and so on, some n into k1 will all be possible electron wave vectors. Now let's look at the frequencies which are not integer multiple of k1. So let's look at, say, frequency of 3.5 into k1. So this we will have 3.5 loops in the length of L, which will look something like this, 3.5. Now we can see that at one of the edge it has a non-zero value. So this cannot be a possible wave vector of an electron. If we look at any other frequency, then we will always see that at one of the edges, there is some non-zero value of the wave function, so which makes it not an electron wave. So now we know that the possible frequencies that the electrons can occupy are K1, which is pi by L, then K2, which is 2K1, which is 2 into pi by L, and so on. So some Kn will be n into pi by L. These frequencies are also known as the states in which the electrons can be. A state is nothing but a configuration of an electron. So in this simplistic case of our one-dimensional crystal, we can directly relate the states to the frequency of the electrons, frequency that the electrons can possibly occupy. You may ask, this is all fine, but like, why are we counting these states exactly? Like, why are they important? So, the answer to this question lies in the Pauli's exclusion principle. This principle states that in one quantum state, a maximum of two electrons can be there, and the electrons need to have opposite spins. So, let's say if I have three electrons in my system, the first two electrons can go to my first state, which is K1 state, but the third electron now cannot be in the K1 state, so it needs to move to the next state, which is K2 or 2K1 in magnitude. Now it makes sense why we are counting these states, because by counting the states up to a certain frequency, we will know how many electrons can be fitted in the particular system. Now let's draw these states as a function of k vector. So let's draw these states in the k space. So the first state will be pi by L, then 2 pi by L, and so on. One observation that we can make in this graph is that the distance between two states is constant. So the distance between the first two states will be 2 pi by L minus pi by L, which is pi by L. And the distance between any nth state uh, and its consecutive state will be n pi by L minus n minus 1 pi by L, which is again pi by L. This observation that the distance between two consecutive states is constant for this one-dimensional lattice is a very important one, and we will use this observation to derive the density of states in the next video. I hope you found this video helpful, and thank you so much.